Welcome to the course Digital Transformation and Technological Innovation. So, we are into our fourth module, that is Tech Advancement and Internet Basics. So, let us continue our discussion from where we left in the previous session. So, in the last session we actually started talking about the innovation in AI chips, right. So, we discussed one or two points that AI chips they are designed to build chiplets, which are something different from what we discussed in case of multi-core chips. So, these chiplets they do not have the processing cores, rather they connect multiple smaller chips on a single base. So, instead of having processing cores, they connect smaller chips on a single base. So, that is one important difference. So, that is why this term was coined chiplets, right. So, multiple smaller chips instead of having multiple processing cores, right. And this is a move away from monolithic chip design, right. So, earlier whether we talk about the single core chip or the multi core chip, the chip remains the same, it is just that either one core or multiple cores are there. But here we are talking about multiple chips themselves and they being connected and forming the chiplet, right. So, separate production for different component that are part of the chips that can happen, compute, memory and IO. So, separate production of these components can happen and they can be linked via ultra fast interconnects, right. So, that there is no issue in terms of speed or performance. So, ultra fast interconnects are there. So, what it does, it takes away the problem of overheating and all that issues, because you are using interconnects and you are using smaller chips, right. So, some advantages come there. So, these advantages we talked about in the previous session, that we are able to bypass the manufacturing limit on chip size. Now, suddenly that limit or the size is no longer a problem. So, chip size is no longer a problem, because we are working with a smaller chip and interconnecting with interconnecting them, right. Production yields better, another benefit, because now the quality of production will be better, there would be fewer defects, there would be fewer broken chips. So, that advantage is also going to be there, and then we are not losing anything in terms of transistor counts. So, massive increases in transistor counts, that is still there. For example, 208 billion transistors in NVIDIA Blackwell. So, which actually follows this which has a AI chip which follows the chiplet design, and you can see very huge number of transistors that are there. So, there is no compromise with the with the speed, and at the same time we are able to bypass chip size limits, and therefore, the heat and cooling issues and also the production quality improves. Then another innovation that is linked to AI chips is that they are also being designed for high bandwidth memory integration and using 2.5D or 3D packaging. So, the packaging is got improved through this design in terms of dimensions. So, instead of across using the horizontal packaging, we are now going more for the vertical packaging. So, vertical stacks. So, what is happening, placement of vertical stacks is happening in this case. So, placement of vertical stacks of memory directly on same package as the processor. So, on top of processor we are placing the memory and memory component, and and following the vertical 2D kind of on top of that. So, 2.5D or 3D kind of vertical kind of dimension we are utilizing, right. So, this is slightly different placement. So, what happens, we get high bandwidth memory because of that, high bandwidth memory integration, just like on top of the processor we are placing the memory. So, this is move away from placement across a circuit board. So, traditional placement was across a circuit board, processor and the memory and the IO. Now, move away from that, instead of horizontal placing we are going for vertical stacking, right. Top firms which are taken advantage of this kind of design, NVIDIA and AMD. So this is something, you will see the term high bandwidth memory integration, and that will give you the signal whether that AI chip is having this as a design feature. Then what it does, it creates a super highway for data, and therefore a processor can actually access lots of data, GBs of data, and at a very fast speed, right, up to 8 TB per second. So essentially it creates a high, it creates a super highway, and that is why this term high bandwidth memory is being used, right, and that helps speed up the whole thing. So what is the another problem that it solves? It solves data traffic jams. Now AI, more often than not, the applications, they work with huge large data sets, sometimes internet sized data sets, also in case of LLMs and some of the recent deep learning architectures. So those for those situations, there is a data traffic jam that can happen. So this kind of design handles or solves or addresses this AI bottleneck that is there, right. So this is one big advantage coming from the chip level designing. Now another design improvement that can be seen in AI chips is that they are also being designed for AI math, right. So what is AI math? So essentially they are using tensor or matrix codes, right, to perform matrix multiplication. So everything in AI can be summed up as matrix multiplication. At the bottom level, essentially it is the matrix multiplication. It is the matrix multiplication, lots of matrix multiplication that are happening. So when that is the main math that is happening in case of AI, why not have matrix codes, tensor or matrix codes, and they would be specially designed to or hardwired to do pretty much this kind of math. So specialized hardware units, essentially these tensor or matrix codes are in a way specialized hardware units, and they are hardwired to do only this kind of math. Now other names that are there: matrix multiply units, tensor codes we already used. So these are some of the names for this hardwired units. And top firms Google and Nvidia. So these are the firms that are looking to, that are using this kind of design feature, right. Then another design feature that we see in case of AI chip is that they are designed for unified memory pool, right. So in unified memory pool, both the CPU and the AI accelerator access the exact same memory space, right. So unified memory pool, so whether if CPU needs some memory for execution, or whether the AI accelerator needs some memory for accelerating the execution, then exact same memory space can be used, and therefore there would be some time that can be saved. So there is a lot more time that is traditionally wasted when we copy data back and forth due to separate pools of RAM for CPU and GPU. So for the CPU and GPU, so whenever some computing is more suitable for GPU, there has to be a copy of that data that will happen from CPU RAM to GPU RAM, and that will take a lot more time, right. And if a unified memory pool is there, then both can access the same memory, both can access the same RAM, and therefore this extra time that is taken in copying data back and forth, that time wastage can be avoided, right. And therefore this unified memory pool, this design feature is something that can be very beneficial. So some of the top firms which are taking advantage of this design feature are Apple and Nvidia. So this was unified memory pool. Now when this design feature is there, so essentially what we are achieving zero copy scenario, and this can be really critical for a real time task where AI can has to immediately use the data which is just fetched by the CPU, right. So because unified memory pool is there, then that is possible, right, otherwise that copy will happen. So essentially this particular design creates a zero copy scenario, zero copy environment. where for real time tasks we see the benefit where AI can immediately use the data fetched by the CPU, right. So, example applications are voice assistants or video processing applications which benefit from this kind of design feature. Moving on, so this was about some interesting features about AI chip designs that have happened. Now another important change in design is AI chip racks. So AI chip racks, they are actually designed for direct to chip liquid cooling. So there is change in the racks also for AI chips. So here, because there is so much of processing that will happen and so much of heat that will happen, so a mechanism to manage that. So these racks, AI chip racks, they are designed for direct to chip liquid cooling, right. And why, how it happens? By placing cold plates directly on the silicon, right. So what it does, it avoids thermal throttling, right. It slows down, slows down the thermal throttling, melting or melting it avoids, slows down the whole process, the overheating process, right. So that is one important benefit, right. And because of this kind of cooling mechanism, direct to chip liquid cooling mechanism, it also enables chip to run at maximum speeds for longer periods. That means, because in case of AI models, you might have to train large models which might be internet sized, and therefore the training will keep on happening and the computing will happen for longer periods, and that can be supported by these AI chip racks, because chips can run at maximum speed for longer periods, and therefore the models, AI models, can converge, and because of that there would be direct benefit. So AI chip racks is another connected innovation here. Now we are moving away from some other innovations that can happen. So innovation in semiconductor materials for the chips. So silicon remains the dominant semiconductor material for consumer CPU and GPU chips, right. And but because of the problems that we have already discussed related to size, heat and cooling, scientists and researchers and tech firms, they were looking for alternative materials which could be used in place of silicon, and some of these size related constraint could be overcome. And in that search, there are some candidates that have been found, and they have been successfully used also in the industry. So alternative materials, some materials have been found, tested, experimented with, which have successfully displaced silicon in certain scenarios. For example, high power, high frequency, extreme temperature applications. Going for these materials might make sense. And so for high power, high frequency and extreme temperature applications, these alternative materials are being used, and they have displaced silicon in those scenarios. So what are these materials? So one is gallium nitride, right. So it has largely replaced, not fully, but largely replaced silicon in consumer fast charging power ICs, right. Fast charging power ICs, which are used for smartphones and laptops. So when higher electron mobility and switching speed this material provides, and because of that the benefit is there, right. So it has largely replaced because of this higher electron mobility in comparison to silicon, and higher switching is speed. Because of that, gallium nitride is largely replacing silicon in these consumer fast charging power ICs, right, and both the computing devices, smartphones and laptops, right. So therefore life of these smartphones and laptops will go up because of this material being more suitable for extreme temperature applications. Now because of this advantage that it can work in extreme temperature application, gallium nitride is also rapidly expanding into AI data centers, because AI data centers are the ones which are continuously being used, and some training might also happen, and therefore there are lots of large language models and applications and frameworks that are running through these AI data centers. So gallium nitride could be better options for as a silicon materials. So all the chips which are actually made using these materials are replacing, right. So also in case of 5G 6G wireless infrastructure, they will also, because the speed would be much higher, and the same scenario will also happen there. So in 5G 6G wireless infrastructure also, it is the gallium nitride that is replacing or rapidly expanding. Now it can handle massive, now AI data centers and 5G 6G wireless infrastructure. Now with this change, they can handle massive power demands in a smaller physical footprint, right, because these infrastructure, they will also be in a smaller, in a, there would be physical limit to these data centers or infrastructure. So but the power demand is huge. So using this chips made out of this material gallium nitride, the they can do a better job, they can handle this demand much better than what silicon based chips can do. What is another option for semiconductor material? So another option is silicon carbide. So silicon carbide in a way has become industry standard for high voltage power electronics in electric vehicles. So it is something that is being used by Tesla in their electric vehicles. So silicon carbide, in place of silicon based chips, silicon carbide is being used and has become a industry standard. What it does, it gives 3 times more thermal conductivity than silicon, right, and so that is beneficial. And EV power inverters can be smaller because of this change, lighter, and run much hotter without failing, because high temperature scenario, silicon carbide can do a better job, and it has better conductivity also, and it can do a better job in case of high temperature scenario. It can be smaller, lighter. EV power inverters, they can be smaller, lighter, and can be much hotter without failing, right. So better, more suitable for scenarios like electric vehicles or EVs. So this is another semiconductor material which is replacing silicon. So we talked about two, gallium nitride and silicon carbides. Moving on, the next innovation is actually connects us to the computing tech itself. So the standard computers that we use, that we have been using for many decades now, so that technology itself can also be replaced with something that is more new or innovative, and supports the future requirements much better. So one such candidate is quantum computing. So quantum computing is something that is believed to be next generation computing or the future of computing. So this is slightly different from the standard computers or the way they work. So it uses the principle of subatomic physics to process information in significantly different ways from standard computers. So what happens in standard computers, the computers that we use, that we have been using for many decades, the way information is processed or coded or processed, quantum computers do slightly differently. They use the principle of subatomic physics to process information. So if we look at the standard computers, they use bits, that means 2 states, 0 or 1. That is something that we have discussed in one of the module, right. And so this is the scenario with the standard computers. Now what is the change in case of quantum computers? So quantum computer use qubits or quantum bits, right. So how qubits or quantum bits are different from bits? So there are more states, more than 2 states, and because of the existence of more than 2 states, there are more possibilities that that can happen, and therefore there can be exponential increase in the computing capacity in case of quantum computer, right. So what are some of the properties that we can observe in case of quantum computing? So one thing is superposition. So in qubits, they can not only represent 0 or 1, they can represent both simultaneously. So this, when they can represent both simultaneously, this we are referring as superposition property. So qubits can represent 0, 1 or both simultaneously. So, therefore, how it benefits the computers or machines. So, machines can explore many solutions at once, right, because of this state, and they can represent both, and therefore twice the computations can happen. And so, machines can explore many solutions at once. So, that computing capacity goes up because of the extra state that can be managed through quantum computers. So, this superposition, this we refer as superposition. Then another property is entanglement. So, another benefit is that qubits can be linked, so that if there is a state of one uh, if there is change in the state of one, it will instantly influence the another, no matter the distance. That means no matter the distance, that means less time will be taken or no time will be taken, we are saying instantly. So, no time would be taken when these qubits are linked, and there is some there is state of one, if it is supposed to influence other, that will happen instantly. So, this entanglement is also there. So, this can benefit and help us achieve faster speed. So, superposition gives us more states, this one gives us faster speed, because instantly the other states will be influenced. Third one is interference. So, machines can filter through different possibilities to find the correct answer. So, this interference that supports filtering, and therefore, machines can explore much better, and that also improves the some of the computing scenarios. Right. So, these are the three important attributes of quantum computing, and that will push the future of computing further. Now, if we look at the current state of quantum computing. So, right now it is at the NISQ era, which is noisy intermediate scale quantum, right. And if we look at the kind of hardware that is there, so systems, they have actually reached hundreds to over 1000 qubits, right. So, and but this still, because still there is noise issues are there in the quantum computers, in the current state of quantum computers, and those systems have reached hundreds to 1000 qubits. They remain highly sensitive to errors and noise, right. And if we look at the examples of the firms which have products in this case, so IBM Condor chip is there, right. So, that is one. So, already there are existing products, lab level products. So, nothing has reached to the consumer end, and everything is experimental in nature and deployed at top tech firms or some government organizations, right. So, current state is still, it is under development, but lab tested. Now, we also observe that in the current approach of quantum computing is actually following a hybrid approach, and in this hybrid approach, what is happening, that most current setups they are hybrid, and what is happening is standard supercomputer is actually doing the two things. First, it is handling the bulk of the workload. So, still standard supercomputer would be doing the bulk of the workload, but for certain specific or complex tasks, it can offload those tasks to quantum processor, right. So, hybrid kind of setup, where standard computing and quantum processor is also there, both work in tandem. So, much of the traditional workload handled by the standard computer, supercomputer, and the complex specific task can be offloaded to quantum processor. So, this hybrid setup is something that is most common currently. Now, if we look at utility, in terms of utility, how the quantum computing is doing. So, demonstration has happened of quantum supremacy in a specific lab test. So, in a specific lab test, the supremacy of quantum has been established, has been demonstrated, but practical everyday use is still, it will take years to reach to that situation. Now, if we were to look at the immediate impact, where whatever the state is, where which kind of application the quantum computing can still be used, where it can have immediate impact. So, most immediate impact is being considered to be on cryptography. So, essentially many scientists they are looking to transition to post quantum cryptography. So, using quantum computer for cryptography. So, and this will also help protect data from future decryption, right. So, to protect the data, post quantum cryptography is something that scientists are looking to transition to. So, this is more immediate impact that is likely. Now, if we look at how the access can happen, if it happens to not everyday end users, but even to some users in labs and scientists and researchers, then it will more likely cloud computing will be the default mode for this. So, quantum cloud computing is the mode that is being used and that will be used for giving access to quantum computing. So, most user access via the cloud services, and because most of the companies which have actually setups, quantum computing setups, they are these top tech firms, right. So, if we look at the examples, then cloud accessible systems, cloud accessible system for quantum computing, they are actually being operated by IBM Quantum, Google Quantum AI and Amazon Bracket. So, these are some of the companies and cloud accessible systems that are providing access to quantum computing. So, that completes our discussion in terms of tech advancement that has happened. So, we talked about quantum computing and current state of it. We talked about the semiconductor material and the change from silicon to gallium nitride and silicon carbide. We also talked about the AI chip racks and different design features that are there in AI chips. So, let us stop here and we will continue our discussion in the next session. Thank you.